In this video, we will be solving this question which says for any two non-zero vectors A and B, we have to prove that the dot product of A and B is equal to 1 divided by 4 square of norm of A plus B minus 1 divided by 4 square of norm of A minus B. So let's begin. We will try to prove this equality by expanding RHS. So your RHS is equal to 1 divided by 4 square of norm of A plus B minus 1 divided by 4 square of norm of A minus B. So first let's quickly revise the norm. If you have a vector A which is equal to A1, A2 till AN, we define the length or norm of a vector which is denoted like this, and this is equal to square root of dot product of A with A. So if you square both the sides, you will get that the dot product of A with A is equal to square of norm of A, where A is any arbitrary vector. So let's apply this concept to this question. Thus, this can be expanded and rewritten like this. That is 1 divided by 4 dot product of A plus B with A plus B. And similarly, this can be expanded and written like this. That is minus 1 divided by 4 dot product of A minus B with A minus B. Now let's solve these brackets. That would give me the dot product of A with A plus dot product of A with B plus dot product of B with A and plus dot product of B with B. Similarly, expanding here, I will get A dot A minus A dot B minus B dot A plus B dot B. Now, we know that A dot B is equal to B dot A by the rules of vectors, and also A dot A is equal to norm of A square and B dot B is equal to norm of B square. So, making the substitution for the same, we get that 1 divided by 4 multiplied by norm of A whole square plus 2AB plus norm of B whole square minus 1 divided by 4 norm of A whole square minus 2AB plus norm of B whole square. Now simplifying this, I will get that this entire expression is nothing but 1 divided by 4 norm of A square plus 2AB plus norm of B square minus norm of A square plus 2AB minus norm of B square. So this and this gets cancelled, this and this gets cancelled, so leaving you with 2AB plus 2AB which is equal to 4AB. Now again here this and this can be cancelled and this is left with the dot product of A and B which is equal to LHS. So we started with the RHS and we reached to LHS. Thus your LHS is equal to RHS, hence proved. Now moving on to the second part which says show that if the set of vectors A1, A2 till AN is linearly independent and C1, C2, Cn minus 1 are any scalars, then the set of vectors A1 minus C1an, A2 minus C2an till An minus 1 minus Cn minus 1 an is also linearly independent. Now we are given that A1, A2, An is a set of linearly independent vectors. So by the definition of linear independence, if you have n vectors, suppose from A1 till An, and these vectors are in Rm space. So these vectors are linearly independent if there exist numbers k1 till kn not all 0 such that you have k1 a1 plus k2 a2 plus till kn an is equal to 0. So if this equation holds only when your k1 is equal to k2 till kn is equal to 0, then the vectors are said to be linearly independent. So a linear combination of linearly independent vectors can only be the 0 vector if all the coefficients in the linear combination are 0. Now we have to prove that the vector a1 minus c1an, a2 minus c2an, and this goes on till an minus 1 minus cnan is linearly independent. So consider this set of vectors and let p1 multiplied by a1 minus c1 dot an plus p2 multiplied by a2 minus c2 an, and this summation goes on till pn minus 1 multiplied by an minus 1 minus cn minus 1 an is equal to 0. So simplifying this, I get that p1a1 plus p2a2 plus pn minus 1 an minus 1 minus p1 c1 an plus p2 c2 an plus, and the summation goes on till pn minus 1 cn minus 1 an is equal to 0. Now again from this component I can take an common, which will lead me to this equation, or this can be further written as like this. Since we have given that the set of vectors a1, a2 till an are linearly independent, then all the coefficient of these vectors must be equal to 0. This implies that p1 should be 0, p2 should be 0, until pn minus 1 should be 0. Also this should be 0. Thus all the coefficients above are 0, and therefore the set of vectors a1 minus c1 an, comma a2 minus c2 an till an minus 1 minus cn minus 1 an are also linearly independent, which was something we were asked to prove.